Welcome to Vector Voodoo, Unleashing the Magic of Vector Databases with Python, which is a title I regretted probably about 10 seconds after I submitted the proposal, but we're here now, so what can you do? Yeah, I guess in terms of who am I and why am I here talking about vector databases, I work for a company called EdgeTier, which I'm sure a lot of you have heard of because we've been standing literally right outside this door all day trying to get people to work for us. But essentially, we are a startup and we develop tools to assist kind of customer care teams. So what we do is we integrate into a load of different chat and email systems, so the likes of Zendesk, Salesforce, Customer, Intercom, all these different systems. We read in all your chat, email, calls, survey data in real time, and then we start to layer on some fancy kind of reporting, analytics and AI on top of that. So we do things like anomaly detection, emotion detection and analysis, kind of semantic search, automatic labeling, automatic agent QA, and all this kind of stuff. There's more there that we do as well. As part of that, I've kind of spent a lot of time, a good bit of time kind of messing around with vector databases to, I guess, build out some of the products that we have. So I've learned maybe a thing or two from doing that I hope to impart on you today. And then also kind of ever since I learned about being able to represent text as a vector in like a simple term document matrix, I've always kind of found that kind of fascinating, and how we can kind of use kind of similarity measures to compare these vectors. It's always been kind of interesting to me. So I thought when I was asked by my company, will you give a talk at the PyCon, that this might be something that I can talk for about 25 or 30 minutes about. So yeah, in terms of what I'll cover today, I'll start by introducing the idea of a vector database, high level what it is, and how we kind of measure vector similarity. I'll then kind of dive into some of the kind of different indexing strategies that different kinds of vector databases will use to query the data. And then finally, at last, I'll jump into some kind of Python examples because I'm sure you're all kind of interested to see that. And then from there, I'll kind of talk about how we use kind of vector databases in the work we do at EdgeTier, and kind of some of the mistakes I've made over the years from working with them, and hopefully things you might consider then to kind of not make the same mistakes. So in terms of what is a vector database, essentially a vector database is a kind of database that's built for the kind of efficient storage and optimal querying of high dimensional vector data. So a lot of the examples I'm going to talk through here are quite simple, kind of low dimension examples. That's really just to kind of help you kind of get your head around how they work, but it's worth just remembering as I go through them that typically we're going to be talking about very high dimensional vectors and a lot of them. So it's important that all the optimizations I talk about are kind of, you keep that in mind as I talk about them. In a kind of more traditional kind of database, like, I don't know, your standard kind of Postgres database or whatever, typically you're going to be querying your data for kind of logical or simple kind of logical operators like where field X greater than Y and field A greater than B. The thing to remember with a vector database is we're always going to be querying the vector database, or typically querying it, to find vectors that are in the database which are similar to the vector you are giving it. So you lamp in a load of vectors, you have some sort of input vector, and you're like, find me all the ones that are similar to this. To do this, we'll use kind of like a similarity metric. Now, there's lots of different kinds of similarity metrics, things like you'll hear the Manhattan distance, the Minkowski distance, Euclidean, L2. They're all different, but they're all kind of really the same. They'll give you the same kind of relative results usually. Typically, the one you'll deal with most is a kind of cosine similarity metric. So what that is kind of doing is it's measuring the cosine of the angle between the vectors. So you can see in my kind of simple example here on the right, we have three vectors. I'll jump here. Oh, this isn't working. I'll jump back here. And we have three vectors, vector A being the green, vector B being the red, and vector C. Oh, thank you. Oh, no, it's fine, it's fine. Don't worry about it. And vector C being the blue. And kind of here you can see that the angle between the green and the red vectors are quite similar, or they're quite small. And you'll see when we run the sklearn cosine similarity function on those two vectors below, we'll get a 0.98 similarity. Similarly, between vector A and vector C, we'll get a 0.2 to 6 similarity. So the closer the value to 1, the more similar these vectors are, and the closer the value to 0 or -1, the less similar they are. Now, at this point, you're like, well, maybe you'll be like, why the hell would I ever want to dump a load of random vectors into a vector database and find ones that are similar to it? The thing is, like, it's worth remembering that these vectors could represent anything. You know, it could be geospatial data, it could be a vector representation of an image, it could be, you know, audio frequencies in an audio file. It could be like a one-hot encoding of a customer's basket at checkout, and you want to find other customers who maybe have similar baskets and what else they bought. In my world, it's usually a kind of sentence embedding or a document embedding of a piece of text. So we'll typically use a model maybe downloaded from Hugging Face or the sentence transformers library. We'll pass a sentence in, we'll get a semantic representation of that text, and then other sentences that mean similar things will have similar vectors, and their cosine similarity will be high, they'll be close to 1. So to kind of jump into a very quick example here to illustrate this, 1 second, I'll just jump over to. Now, I should say I'm not a front-end engineer, so this graph on my website looks crap. But here you have a kind of very simple example of, you know, movie descriptions encoded in a kind of 2D space. So over here on the top right, you can see we have kind of Christopher Nolan Batman movies descriptions, and these will all have kind of like similar vector representations using a sentence encoder. Down on the bottom right here, you'll have a couple of Tarantino films in, Inglourious Basterds and Pulp Fiction. At the bottom left here, we have a couple of Godfather films which have very similar descriptions. Over here, we have Scorsese with Goodfellas and The Color of Money. And then over here, we have Shawshank Redemption, which is less similar to any of these kind of movies. So you can see how these kind of sentence transformers can encode the kind of similarity between the meaning of these sentences quite efficiently. And then if we passed in, I don't know, the Godfather 3's description, we'd expect its vector to sit somewhere down here. So hopefully with that, you can have an understanding of roughly what a vector database does and how it might be useful in the context of text search and things like that. In terms of how do they work then, so in a normal database, when you insert rows into, you know, a table that has some amount of columns, we'll typically define an index on, I don't know, maybe an ID column or a date column or combinations of columns. And then when you query that using one of the logical operators that I spoke about earlier, the database will basically go, let's say, for example, you have a database of employees and their age and nationality and things like that. And you want to be like, oh, give me all the employees where the age is greater than 25 and the nationality is Irish, and you have an index on both those columns. The normal database will go, okay, yeah, I have a pointer over here to all the ones that are people who are over 25. Here's the pointer to all the people who are Irish. Now let's do any other filtering you want on that data. In a vector database, though, we're kind of indexing the data slightly differently because we want to index the data in such a way that when we pass a vector that's in a similar position to your input vector in this kind of vector space that we've created, we need to be able to quickly and efficiently find out where in that vector space that is and which other vectors are kind of most similar to it. Now, the indexing strategy used will be quite different between database, and I'll talk a bit more about those on the next slide. To dive into a few of these kind of different indexing strategies, we'll start with the kind of most simple one, which is called a flat index. And essentially, this index does nothing. All it does is it lashes every vector that you have into the database, and then when you want to find what vectors are similar to that, to an input vector, it compares it to every other vector in the vector database. So this is the equivalent of essentially, you know, you have a pandas data frame of sentences. You might use a sentence transformer to encode them all, and then when you get a new vector, you'll go, okay, get the similarity to everything in this pandas data frame, sort by order descending, give me the top 10 results. Now, you can see how that just won't scale well past, you know, maybe 10, 50, 100 vectors, depending on the dimensionality. And, you know, if you're building any sort of real-time, maybe semantic search system, you can't really use this. But that being said, there is a place for these kind of flat indexes as well, and potentially retrieval augmented generation is one of those. If you have a, you know, maybe a very small FAQ, like set of FAQ articles that you want to generate responses based off, a flat index can work here. And I think most of us in the room will be able to implement a flat index using something like pandas or a dictionary or whatever you want to use quite easily. As we start to I guess, maybe scale up what we might use a vector database for, we need to find optimizations to make to kind of query the data more quickly. And the first one of these I'll talk about is an inverted file index. And essentially what this will do is when you load all your vectors into the database, you'll index it. And what it will do is it will partition the vector space that you have into a number of clusters. It'll do this essentially using a kind of k-means type of algorithm. So you can see here we've kind of split this random kind of simple vector, 2D vector space into about 15 different partitions. And if we say have this query vector A, we will first find out what partition does query vector A fit into based on its proximity to the centroid of that cluster essentially. And then once we find out what cluster it's in, we'll just compare vector A to the other vectors in that cluster, which you can see like in, when you're dealing with a much larger set of vectors or maybe high dimensional vectors, this is much more efficient in terms of the speed and the computation required than the flat index. But I'm sure maybe some of you can see right now that if you look at vector B here, which is probably the most similar vector to vector A in our example, that would not be captured here because it's weak at the kind of cluster boundary. So while this is a big improvement over the flat index, it is kind of quite inaccurate around the cluster boundaries. To kind of combat that, there's another kind of index which is called locality sensitive hashing. Now, this is maybe the most complicated one to explain, so apologies if I make a mess of this, but this works not too dissimilarly to the kind of inverted file index that I spoke about before. And I have 3 examples here, but if we focus first just on this graph on the kind of top left here, essentially what we do here is we draw a number of kind of random hyperplanes across arbitrary positions in the vector space, and then we create a hash map of where each vector in our vector space sits relative to these hyperplanes. So this hash map could be as complex or as simple as you want it to be, but let's say, for example, in a very simple case here, we might hash each vector with a 1 if it's above the line and a 0 if it's below the line. So vector A here would be hashed with 1 because it's above the blue line, 0 because it's below the red line, and 0 because it's below the green line. Vector E would be hashed with a 1 because it's above the blue, a 1 because it's above the red, and a 0 because it's below the green. Whereas vector C would be 1, 1, 1 because it's above all 3 lines. Then, when we get a new vector that we want to query the database with, we will calculate its hash map relative to these hyperplanes and just get the similarity to the vectors that have the same hash map. Now, you can see if we just do this once that this has a very similar weakness to the inverted file index that I spoke about on the previous slide. But in reality here, we are creating multiple hash maps. So like I've created 3 for this vector space. So in each of these hash maps, I've drawn 3 separate hyperplanes, which will mean each vector in our database is hashed 3 times. So when we get a new kind of input vector, we'll create 3 hashes for that input vector and get any vectors from the 3 hash maps that have the same hashing essentially. So we'll be comparing it to 3 sets of vectors rather than just 1. You do need to kind of find a balance here between how many hyperplanes you're drawing and how many hash maps you're creating, because you can imagine that if you scale this up and have, I don't know, 1 million hash maps with 1,000 hyperplanes in each, that it won't scale well, it'll be slow, or you won't get kind of accurate results there. The final kind of indexing strategy I'm going to talk about, and I really didn't want to talk about this one because I find this sentence extremely hard to say, is hierarchical, navigable, small world. That's the first time I haven't messed that up practicing this. And it's probably the most kind of commonly used indexing strategy. And essentially what it does is it creates a kind of graph at a very low level where each node on the graph will represent a vector or a set of vectors, and the connections between those nodes will represent the similarity or the average similarity between the vector or the set of vectors. What you then do when you have that graph is you aggregate that up across several levels. At each aggregation, you're mapping what the vectors on the lower level will map to in this aggregation, and it forms essentially like a tree-like structure. From then there, when you have like, a fully aggregated tree and you have a new vector that you want to search the database against, you'll get your query vector, like the one I have in pink here, and you'll start at the top level and you'll go, okay, which of these entry points is it most similar to? In this case, it's the orange one. You'll go into the orange one, get the ones that aggregated up or mapped up to that kind of high level orange vector in our aggregation. You'll find at the next level which of those is the most similar to, and you'll keep doing that process until you get down to the lowest level and you find which node or which set of vectors it is most similar to, and then you'll return the kind of results or the vectors in descending order or whatever way you want to find the similarity. They're the kind of four main indexing strategies that are used or that are worth knowing, at least in my experience. I would say that while I've maybe wasted or spent 5 or 10 minutes talking about this, you kind of don't really need to know this. Like if you're setting up a vector database, it will just handle all this for you. You might be asked, there might be some default value like HNSW when you're setting it up, but most vector databases will just handle this for you. So it's not something you need to know. Hopefully you'll never have to build this from scratch. If you do, I'm sorry. But it's just maybe worth knowing how it's working kind of under the hood. In terms of maybe diving into some Python, because when I made these slides actually last night or the day before, I made a whole deck and then I realized I didn't actually have any Python examples in it. And I was like, oh geez, if we're going to PyCon, I best put some Python in it. So I'm actually just going to show 2 examples of how we can insert data, create an index, insert, and query data using 2 different kinds of vector databases, and they're the 2 I would work with the most. The first being OpenSearch, and the other being PG Vector, which is essentially a Postgres vector database extension. We use those kind of in edge tier, mainly because I guess we use AWS as our cloud service provider, and setting up an OpenSearch cluster was just super simple and super easy to scale up and down, that it was a no-brainer rather than trying to install some sort of other third-party software on an EC2 server or similar. And then we've started to use a lot of PG Vector recently just because it works nicely with the other stuff our kind of main API is doing. So if I kind of just dive through the code here, starting with OpenSearch, we will first begin by creating an index, or what we might think of as a table in a normal database. And we do this with a simple kind of put request. So first we define where our OpenSearch cluster is running, which is some OpenSearch host. We give the password, the username, all that kind of usual stuff. Then we define the kind of index body, which all we're really doing here in the settings when we say the index KNN equals true is we're saying this is basically a vector database. That's what that's telling OpenSearch to do. And then we're saying what kind of similarity measure we usually want to use here, which is the cosine similarity. From here, we then define the fields that we want in this index or in this table, which, I'm just using the kind of simple example I shared earlier with the kind of film descriptions, and we just have to define what dimension we expect the vectors to be, which, since we're using this all-mini language model, this outputs, 384D. So we just specify that so the vector database knows how much space to assign there. Then if we want to insert a few documents or a few vectors into our database, we simply, you could have these in a data frame or a dictionary or whatever format you want. We simply loop through them, map each of these fields to what, column or field this maps to in the vector database. We create the vector using our kind of sentence transformer, and then we simply send a post request to the OpenSearch cluster to insert them. And you see here, we pass the document ID and the index when we're doing that. Then, if we want to query the database, we get some new description, say our Godfather 2 example here. We'll follow a similar process to vectorize the movie description. We'll create the search body, which basically says we're doing a KNN search on our index, and this is the vector we are giving you to search. Then this will return a number of hits, which is what it's called in OpenSearch, which I always find kind of funny. And from that, we'll just, in descending order, we can print out the results. If we switch over then to a kind of PG vector example, and this is kind of like, I've done this in a way that might sit inside a Fast API app or a Flask app or some sort of API like that. I've actually left out the instruction here on you'll need to install the extension in your database, but that's just a very simple command. If you Google PG vector at all, it will come up straight away. We'll then create the table using kind of like an Alembic upgrade. So here I define a very simple upgrade. I'm saying we want to create a table called films. We'll have, these are the columns, the ID, the film, the year, the description, and then the vector. And you can see we use this PG vector library to define the type of this column in our database. We'll then, somewhere else, maybe in our API repo, we'll define a database class that we can use to interact with this table in the database. And again, this will just have the same columns that we've defined in our table. And then, actually, I really like, it's quite easy to insert the documents then into the vector database. We simply create a session using SQL Alchemy by connecting to our Postgres database. We'll create a film class for each document in our dictionary or list or pandas data frame, whatever you want to use. We'll add it to the database using the session, and then we'll commit. And that inserts your 3 film descriptions along with our vectors into the database. Then similarly, if we want to search for vectors that are similar to our input, say our Godfather 2 example here, we first begin again by encoding the description. We'll then use the same database session to query the films table. Say we want to get the title, the description, and the cosine similarity, which in this case is 1 minus the cosine distance. We'll then perform that, like specify that, say we want to order it by similarity, and we'll use the .all kind of method to get each result as a list, or in a list, I should say. We can then iterate through that set of results to print out whatever we want, or I don't know, maybe move them somewhere else or surface them to a user through an interface. So yeah, that's just a kind of couple of simple examples to show you how easy it is to kind of maybe get started with PG Vector and OpenSearch. I thought I lost us there. In terms of what we do at Edge here with vector databases, so we actually have a few different use cases for it. And the first one that we kind of started with was this kind of semantic search engine. So essentially what we do here, and it's in this graph at the bottom here, when we get a new message into our system, we put it on an Amazon queue. We have a separate service that picks up this sentence or this message, vectorizes it using a sentence transformer model, and inserts it into our OpenSearch cluster. Then what we can do is we can allow the users, sorry, I should specify as well that when we encode these sentences, we use a multilingual transformer. So this is a model that understands I can't log in English is the same as, well, someone tell me what that is in French, but it understands that it's the same in Spanish, German, etc. So what the user can do is they can search in our system for, oh yeah, show me any time over the last 30 days where people have said something similar to I can't log in, and here you can see across the bottom, you can very easily see the kind of trends there. So maybe something was happening here. And that's all driven from our kind of OpenSearch cluster. Kind of from here then, we developed what we call a kind of phrase tagging system, and this uses the exact same database, but essentially what it does is it allows our users to kind of configure a phrase or a set of phrases that represent a particular topic that they might want to track over time or be alerted about if a message comes in like that. So you can see in my example here, and I understand it might be hard to see, but I have I'm going to contact my lawyer here. Hello? Oh yeah, it's working. So we have here, I'm going to contact my lawyer, and this is searching our vector database on OpenSearch for any sentences that are similar to I'm going to contact my lawyer. And you can see that we have a lot of stuff here in different languages, and it's not exactly the same as what I've inputted. So we're doing this kind of like semantic matching. And this is very useful because not only can we then start to tag these messages as they come in real time, but we can also allow the users to set up an alert. So the next time someone says, je vais contacter mon avocat, or whatever it is in French, that they'll get an email to say someone's going to sue you, basically. Then kind of off the back of that, in the last kind of few months, because everybody is talking about LLMs and things like that, we've started to do a lot around kind of retrieval augmented generation. And this is really where our kind of PG vector use cases come in, because it's just easier for us. But essentially we're doing two things here. So we started by essentially generating auto responses to emails or suggested responses to emails for the agents to help them speed up essentially how the handling time for writing back to kind of email contacts. So what we do here is when a new email comes into the system, we'll remove any noise from the email. We'll figure out what are the 2 or 3 points that the customer is really looking for an answer on. We'll then compare that, we'll vectorize those 2 or 3 points, and we'll compare that to like an agent guideline or FAQ document that we have in a vector database. It's worth noting that in this case, we actually use a very simple kind of flat index for this because there's never really more than 50 or 100 documents there, so we don't need anything more sophisticated. But what we do then is essentially we find whatever 5 or 10 most similar kind of suggested responses based on the agent guidelines, and we pass those to a large language model along with the input email to basically say, give us a response to this, please. And the model goes, yeah, here you go. Now we do pass in additional rules related to the business and stuff like that, so it's not going mental. Off the back of that then, we started to do some stuff using LLMs around contact reason labeling. So this is where we'll analyze essentially a full chat or a full email conversation or full call transcript. And we will essentially try to assign a contact reason to that. Now, some customers we work with who are great only have maybe 10 or 20 kind of contact reasons, which is quite easy to manage. But some of the more, I guess, larger kind of customer care centers that we work with, they might have 50 or 100 or 120 even granular contact reasons, and they really want quite specific tagging on these conversations. So it's computationally and fiscally, I guess, not viable for us to pass 120 contact reasons along with descriptions and examples through a large language model with every call or chat that comes through their contact center. Not only will it cost us a lot of money and cost a lot of computation, but also the large language model's context window might not be large enough to even understand what we're giving it. So what we essentially do here is we start by following a similar process to what we do with the emails. And we remove any noise or anything like that from the conversation, try to identify what the main kind of contact points are or the main points are from that contact. We'll compare that to the list of contact reasons that we have in a vector database with the examples, and we'll get the 5 or 10 most similar examples, and then we'll just pass those to the model. So essentially what we're saying is, here's a call that happened in this contact center. Here's the 5 topics we think it's about. Will you just tell us which one it is? And the model goes, yeah, no bother, it's cancel booking or delete account, rather than going, here's 100 topics, will you give that a read and let us know which one it is, and then we're waiting maybe 5 minutes for it to come to an answer, which might not even be accurate. In terms of then maybe some things I've learned from working with vector databases in my time at EdgeTier, yeah, I guess the first one is consider dimension reduction. I made an absolute dog's dinner of our semantic search system when we first went live with it. I was lucky we got the kind of Series A funding right afterwards because I wasted a load of money on it. But essentially, I thought that we would need to store all 768 dimensions that the vector transformer was giving us to maintain the kind of level of accuracy that we want for this kind of semantic search and phrase tagging system. And at the time, we didn't have as many customers, or the contact centers we were dealing with were of a moderate volume. And it worked fine, but as we kind of scaled up our customer base and the amount of data we were storing doubled or tripled, this quickly became a problem and everything started to slow down. So we underwent a huge task of reducing the dimension of the vector that we store from 768D down to 64D, and now it works so much more efficiently. It's just as accurate, and yeah, it's just way better overall. So I would really recommend doing that. In terms of dimension reduction on strings, or sentence vectors, I should say. We messed around with things like UMAP and PCA and stuff like that, but really we found that actually a simple random projection just works fine and is very easy to implement and very quick to run inference on. So I would recommend that. Another thing to consider, particularly in the domain of kind of semantic search, is whether you need to store a vector representation of a short string. So, if you're ingesting, say, customer contact data and you have a message that just says hello, and you have another message that says, hello, I'm contacting because I can't log into your website and I'm getting a 404 error. Both the vector representation of both of those pieces of text will be the same size. They'll both be 64D, 380D, 768D, but one of them contains a lot more useful information and the other one contains essentially no useful information. So you kind of have to consider, is it worth storing all the vectors that you might get? Can you get away with, oh yeah, if a string is short, let's just not store that. Is that even interesting to people? Think about data retention. So kind of what I was saying in the first point, these kind of vector databases can get quite expensive quite quickly. And obviously vector data is quite rich and typically bigger than standard kind of integer IDs or short strings or whatever. So, you might not need to store a year of data or a month of data or a week of data. For our semantic search system or the phrase tagging system that I showed you, we really only need 2 weeks or a month of data depending on the customer that's working with it. So we can kind of manage how much data we're storing and the kind of computation power we need to host and query that data effectively by having a data retention policy. And actually, one of the things I really like about OpenSearch is you can set up what's called, I think it's an index lifecycle management policy. So what we do when we index the data is we create a new index for every customer every day, depending on when the message was sent. So all the messages today go into an index for customer A, date, what is it today, the 16th or something, or the 15th, and then all the vectors for tomorrow will go into an index that's like date tomorrow, customer A. And what you can do in OpenSearch is when you create an index lifecycle management, you can basically say 30 days after you create this index, delete it. And it will just handle all that kind of deletion automatically, which is great because you don't even have to think about it. So I'd really recommend using that if you're getting started with vector databases. And then the last thing, which is probably contradictory considering I've spent the last half an hour talking about it, is you might not actually need a vector database for what you're doing. So like the kind of simple RAG stuff that we were doing, the first couple of customers we worked with that on, the vector database was just a pandas data frame with a column that was vector. And we were able to like very quickly, essentially get the system up and running using a kind of hacky version of a vector database while we figured out where we might run into issues either with the kind of data we're storing, additional data we might need, and kind of how many vectors we might be storing. So I'd recommend kind of just thinking about that before you dive into any projects, especially around kind of retrieval augmented generation. So yeah, so to kind of conclude, vector databases, incredibly powerful, incredibly cool, quite complicated, but a lot of the tools will do it for you. You can build kind of cool applications such as semantic search systems, retrieval augmented generation, recommending systems, auto tagging systems, all this kind of stuff. There's a lot of different vector databases out there. I've just showed you two, OpenSearch and pgvector. There's other things like I know Weaviate and PyCon, they're big players in the market. They all have quite good APIs and are very easy to set up in Python.
I have a question on in which scenario situation using a vector database is the way to go and any other option will be suboptimal, and in which kind of scenario definitely vector database is not the way to go.
Yeah, actually, I'll talk into this. So yeah, kind of similar to what I was saying, the kind of last slide there. Really, if you're not dealing with, thousands of vectors that are, highly dimensional, maybe, 100 plus dimensions, maybe thousands of dimensions, you can get away with not needing a vector database. Like, for example, that retrieval augmented generation system I spoke about, I think we're storing maybe 120, 200 vectors in a kind of very hacky kind of pandas data frame approach. In a live system that we don't need a vector database for because it's working fine. If we were to scale it past that, like say for example our semantic search system, we know we're going to have, like in there now, I think we've 14 or 15 or 16 million vectors sitting in there. So like there's no way we could run that in a kind of standard database or whatever. So once you get to the stage where you're dealing with the hundreds of thousands or millions of documents, I'd really recommend a vector database, even thousands to be honest. So yeah, hopefully that answers your question.
Before you store any sort of personal information, do you redact it? Do you redact personal information before it gets stored in the vector database? And if so, what impact would that have on the results? Yeah, so what we tend to do is we do have a number of masking kind of algorithms that we use just as part of our kind of standard data ingestion process. So that gets replicated not only in the vector database, but also in the kind of normal data that we store and is searchable in the system. It actually works, I think, to the benefit of the vector database sometimes, especially if you see like people's names mentioned and things like that. Sometimes what you find is that the kind of vector encoding model can maybe pay too much attention to person's names. So, if you're like, oh, show me where Bob wanted a refund or something, or hi, my name is Bob, I want a refund. It might find, other queries related to people whose names are Bob that maybe aren't necessarily related to refunds. So in the context of what we're doing with vector databases, that kind of masking actually works quite well and it really helps things out.
Will the choice of the vector database affect the performance of systems like retrieval augmented generation, like using different vector databases? Or is it the same thing?
I guess it would. Like, I mean, if you're using maybe like if you have maybe a very large, I guess, corpus of vectors or really large set of vectors, using a kind of vector database that maybe is set up with kind of, say, a flat index would be suboptimal compared to like something more sophisticated that uses one of the other indexing strategies I spoke. Now, to be honest, like really you're not going to be going and installing some, random hack job vector database that someone might have made and put on GitHub that has maybe 2 stars or something like that. If you are looking to use a database, you'll probably use something that's more, reputable or has more contributions or whatever. So at that end of the kind of like options available, there probably isn't too much of a difference. But to be honest, like we haven't really done that comparison in terms of retrieval augmented generation yet. So I can't say for certain, but really at the top end, they would be all quite similar.
Hi, I'm just wondering about the dimensionality reduction you mentioned.
Yeah.
You got it down to 64 from 900 plus.
Yeah, 768, yeah.
Or 7, sorry. Is there an inflection point, or how did you get to that? Was it just trial and error, or did you have a methodology?
It was kind of trial and error. So essentially what we did was we took a set of vectors that were similar or had similar meaning in our 768 dimension space and compare the average similarity between those. And then essentially we tried a number of different like levels of dimension reduction. So we went whatever 768, 512, 128, 64. Try to keep it as multiples of 2 because if there's one thing I've learned doing data science is when something's a multiple of 2, nobody will ask you questions about it. Until we got down to around 64, which was, we were looking for something sub 100 and preferably sub 80. And once we got to 64, we found that like the average similarity was still within 5% difference at that level. Once we got down lower, that started to increase. And for our use case around the kind of phrase tagging and the semantic search, we really didn't want that much of a difference. But the less than 5% was okay for us. You know what I mean? It was still within the realms of decent accuracy. So for the performance benefits we were getting at that level, we decided for 64.
Purely in terms of optimization, usually the high dimensional vectors are pretty huge in data. So what sort of optimization techniques would you use to balance memory usage and computation speed?
In terms of deciding to store the vectors or to store the vectors? So the optimization we would use would be that like dimension reduction technique that I spoke about. Because yeah, as we kind of found was with those kind of larger dimension vectors, they just required a lot more, I guess, compute power to insert into the database and index and then also read. And because we're kind of indexing and reading sometimes at the same time, or we're always indexing essentially, and most of the time we found just at that level, at the kind of scale we were doing at, it became unsustainable. So that's when we looked at the kind of dimension reduction as a kind of optimization. Now, really, like I should say that, that was just the final step. Most of the optimization is done that I would have spoke about earlier. But yeah, the dimension reduction and the not storing kind of short strings were the 2 main kind of optimization steps that we made.
Okay, thank you so much.
Great. Thanks, everyone.
Applaud for Paul.